Welcome to the March edition of the CppAfrica Discord Meetup. This time round, we want to talk about iterators. And for those who have been following us before, will know that I did give a version of this talk in November of last year. This is a revised version of the same talk. And I would like to say that I have changed a few things. I've tried a different approach. So even if you did watch the previous one, you should be able to gain something from this one. So I'd like to start with a brief introduction to set the stage on what I'll be talking about and the idea that I had for this talk. So iteration is all about repetition. And one of the things that computers are really good at doing is repetitive tasks. Like when you think of how a computer is spec'd, the processor, you hear that it can do, it's as 3 point something gigahertz or 1.2 gigahertz, meaning instructions per second, meaning that it can do a lot of things very fast. And iteration is the foundation of taking advantage of that. So we have previously had last month's session we had a talk about CUDA's tools, which is like an NVIDIA tool set for programming with their GPUs and coordinating between your CPUs and GPUs. And even in the course of that, I brought up the matter of learning how to do it, learning how to do the same thing, just using the standard library as a starting point for learning. So I thought to redo this talk as a foundational model for work that has to do with repetition. So I'll take a tour of the history, or rather the foundational elements of iteration. I've tried to use a lot of assembly to explain the point, so as to form a foundation for the use of iterators and to explain exactly what iterators are. So first question I'd like to bring up is, what are iterators? I just mentioned a hint that yes, iterating is synonymous with repeating. So I'd like to take a look at the definition of what the CPP reference library says about iteration. So there is a page on CPP reference that does touch on this. Perhaps let me just guide you on how to get there. I hope you can see the browser window. All right. So there is the famous website cppreference.com, which in previous talks I've mentioned it as a source of tools that you can use for learning about C++. However, being that it is a manual, it is very technical, but under the right guidance, I think it should be possible to navigate and learn a bit about programming, even if, say, for example, you're starting from a situation where you may not be able to afford all the big books from all of the big authors. Just having access to this site is a way to investigate and take a tour of different elements. So there is, like on the main site, there are many large topics, and today's topic is iterators, and there is a library for iterators. So if I go there, generally, I like to, when I'm investigating and using this site for that purpose, I usually just like to look at the top like what is it? What does the top sentence say about a thing that I'm looking at? For example, in this iterator library, we say it's a generalization of pointers that allow a C++ program to work with different data structures, like containers and ranges, in a uniform manner. That, of course, to somebody who is new or just coming in, is a bit complicated. But what I like to do is, kind of like navigate using the, like some of the things that I mentioned, say like pointers, and, just have a look just at the top, like not going too far down, but just having a look. So pointer declaration declares a variable of a pointer or a pointer to member type. Okay. So just having a look. So this definition is a little bit complicated, as for somebody who is trying to really understand what exactly do you mean by that, like what are pointers, what exactly is that all about. So to make sense of this definition, like I said, there's a journey that I want us to go through to try and see if it can shed some light on what exactly that definition means. So it's something we will come back to. But a high-level answer to what iterators are is that it is a link between where data is stored to algorithms, and algorithms meaning programming logic and machine code that operates on that data, and a lot of the time at a very high speed. So it's the linking between those two concepts. So I want to start the journey by digging a little bit into what repetition is like in computing, like an idea of how it's implemented. And I want to say that, you see, when we write programs in languages like C++ and these high-level languages, it has to be translated to the actual programs that have been embedded in the processor of the computer. Like the x86 architecture, which is what most computers use, has certain hard-coded instructions that actually take what we feed it and produces the outcome that we want. So repetition is one of the things that is actually really deeply embedded in the CPU of the computer. So when we write code, there are many languages whose foundation is the C language. So the while loop in those languages generally will look the same. And so here's an example of what the typical while loop would look like. We have to establish a variable, or like something, a place where we store the position of where we are counting. So the first time we do something, the position will be 1. Second time we count, the position will be 2, 3, 4, and so on. So it keeps going like that until a predetermined point has been reached. And that predetermined point, if you observe on line 5, we start with a statement that says while, then in the brackets is a condition. And the condition states that if counter is less than maximum, meaning that while the counter is less than the maximum, do the following things. And on line 8 is a very important part of this statement, or rather this code, that we need to increment the counter. Without line 8, the program will just run forever, doing whatever is within the curly braces, which indicates the instructions. So on the right is the equivalent machine code. I'll get to line. Now we're focusing on what is on the right, which is the assembly code, which is kind of like a one-to-one English version of what is actually embedded in the CPU. So, like I said, I'll get to lines 2 and 3 later, but the point that I just want to bring out at this particular point is that the C language or the C style of writing code is very closely related to what actually happens in a machine. It's a high level language, just but only slightly higher. So like on line 4, we see an instruction. The instruction is the first 3 letters, the MOV, or the push, or the first column. Those are the instructions. And what is on the right side are the operands to that instruction. So, for example, on the left, line 2, when we say int counter is equal to 0, we are saying that we are assigning the value of 0 to this thing called a dword, PTR. PTR is actually short for pointer, but we'll get more into pointers a little bit later. So this thing called counter on the left, the machine doesn't need that. That's just for us as we read code. But it represents a place in the memory of the computer where we store the value. Then we come down to the while instruction, so to speak. It is translated into some of the code. I don't want to go too much into explaining, but just as a high level, this jump means jump to this allocation with this particular name. So on line 6 we have jump to L2, meaning that the program goes one step at a time. The first line 4 and 5 is to establish the values which are equivalent in the code on the left, line 2 and 3. But the looping bit is carried out between this line 2. As you can see, there's a move instruction and a compare instruction. Now the compare is equivalent to the count is less than maximum. And depending on the result of that, we either jump back to L3 and continue the processing, or we continue on to pop and the program ends. So this is like the basic of what looping or repeating a task is like. And we do write very many loops. A lot of the programming we do actually just involves a lot of looping. Start from here and end here. Keep doing this particular set of instructions. A closely related, or rather like, I'll call it an improvement on the while loop, is the for loop, which is essentially the same thing. Actually, if you observe the actual machine code that is generated, it is literally exactly the same. What the for loop does is that it contains the bits that control the loop within one block. So it has these statements within it. So there's a for instruction, then there's a first part. There are 3 parts separated by 2 semicolons. The first part is for initializing. So you see we do int counter is equal to 0 and maximum is equal to 10, which is similar to the while loop, which we were looking at before. Then we have the comparison, which is on line 3. I've put them on separate lines just to make it fit. But usually sometimes you can put this on the same line or different line depending on what's going on. Then we have the plus counter, which is equivalent to what is on line 8 in the while loop. So the machine code is exactly the same, but how we write it or how we represent it can be a little bit different. There are some advantages to doing this with the while loop, and one of those is that the variables created for the body of the loop don't leave the loop. The moment the loop is done, we don't have any counter hanging around. But for the while loop, we have to have the variables outside, which can be a little bit unsafe or error prone. So one of the core things that I would like to cover, especially as we head towards dealing with iterators, is the issue of data types of data, and how they are stored or how they are treated when in the computer. So C and C++ are strongly typed languages, and there are other strongly typed languages, but I'll just narrow it down to C and C++ for today. A type is it is a way we specify a real world concept. For example, we've been in the previous code, we're talking about integers, which is a number, a whole number. So there are some hard coded or hard established ways of dealing with the different kinds of concepts, and in particular, there are some fundamental types that are actually even inbuilt into the CPU, and ways of dealing with those types of numbers are different. So in computing, one of the core concepts that is like actually really embedded into the CPU is the issue of whole numbers versus fractional numbers. Whole numbers have their own way, like how they're stored. They're called integral types, and they also have ways that they're calculated. They're actually different pathways in the CPU that if it sees this is a fractional number, then it will take a different path. If it sees it's a whole number, it'll take a different path. There is the concept of registers, which are very short-term memory, which are used in the calculation. And if I could go back to this previous slide, these things that you're seeing called RBP, RSP, is any EAX, those are registers. Those are very specialized bits of memory that are on the CPU that are used for calculation and whatever processing that we need to do. So one of the things I wanted to illustrate about all of this is the matter of how much space is required for different types of data. Integral types have a certain size. The most commonly used type is the integer, and on today's 64-bit computers, it occupies 32 bits, which is 4 bytes. That's what it's programmed to do. There are other types, such as the character type, which takes up 1 byte, which is 8 bits. And there are bigger integral types, which take up a certain number of bits. So just want you to hold on to that even as we go forward, because it's very important to what we're trying to talk about, which is iterators. I know I've not mentioned, or you've not seen any iterators yet, but we'll get there. So another very important notion I just wanted to bring out is a matter of literals. And according to CPP reference, these are tokens of a C++ program that represent constant values embedded in the source code. So back to where we were, where you see like numbers like 0 or 10, those are like actual values that are, they represent themselves, and you can literally see them in the assembly, that they're actually embedded as part of the instruction. Though the names like counter and maximum, like I said before, those are for the programmers. It's for communication between programmers. But in the machine code, such values are actually embedded as part of the machine code. So that's what literals are. So whenever you read a program and you see something like one is equal to, I mean, a certain variable is equal to 4, the 4 is a literal which will be copied as it is into this machine code. Then we have the notion of variables. And variables represent like a place in memory. When we write our code, we give it a name just for our own memory, but it represents a place in memory that can store a variable of a certain type, meaning that its value can be changed in the course of the program. It's just a bit of memory that in the course of it, different values can be put in. So, for example, here we have int counter equal 4. So the counter space can store any integer. And as we saw, like in the loop, there's the counter variable is where we store where we currently are. And it's read as part of the loop, like what is the current value that is stored here. But the important bit is that you need to give it a type. The reason why like C and C++ are strongly typed languages is the notion that you need to define how much space the variable or the information that you're putting will take. Yep. So in the examples above, I mean, I mentioned that int is 4 bytes, which is 32 bits, and a character is 1 byte, which is 8 bits. So a pointer, now we can kind of like get like, like a little bit into what a pointer actually is. It's a special data type that is like an integer. It represents a location in memory. Yeah, like in the computer, we can't have 0.5 memory. The memory has to be well defined as a whole number, and that's usually stored in integral types. In actual sense, like the reason why you say there's something like a 32-bit computer, that defines the size of how much memory is required to store an address of memory. So when we write our programs, we need to have this notion of, or sometimes, like in some cases, and we need to know where something is stored. So for example, if you have a variable, in this case, say integer is 42, the integer represents a certain place in the memory, and we store the value 42 there. On the next line, we store a pointer. See, we call it int pointer. So that location stores the memory address, but it needs an extra piece of information. It stores the information on which type is stored in that particular location. So let me see, just copy this link just for a moment. I did try to prepare some Godbolt links for some of these examples. And so the point I'm trying to illustrate is the difference between a type of a certain kind, so I'll give it a moment. Okay, I'll go back to the slides in the meantime, but because it seems access to the site is slow. But generally, it's the same kind of code that is running there. So the pointer to integer, the value that is stored there will have a weird value. But if we print, you see there's some two print statements here. One, on line 4 is a statement that prints the value of integer, which would be 42. And the value, in line 5 is a statement that prints the value of the integer, or the pointer to integer. And you'll get some weird value, but we'll demonstrate that as we go ahead. So I've talked about single bits of memory, places where you store one integer and the computer knows how to work with that. There's the concept of storing groups of a certain type, say like a group of integers, which is very instrumental to the computing. And there's this structure called an array, which generally represents a section of memory where one variable has been, or rather a group of variables have been stored, meaning that the computer must figure out some space for them, knowing that, for example, each say integer is 4 bytes. So if we store 10 integers, we'll have to allocate 4 times 10, which is 40 bytes of memory in order to store that array, and we give it a name just to refer to it in our memory. But just like what we're talking about before, the computer doesn't quite care about names, it just cares about addresses. So variable names usually correspond to addresses in memory. So when we translate the program, it all goes away, and all we have is addresses, which the computer is able to just dispense with and deal with very quickly. So based on what I just described, the way when you have that one variable that describes a range of memory, it's possible, or rather we use offsets from the beginning to refer to elements further down the line. So if you want the 5th element of a group of 10, there's a notation which is like within square brackets, so the name of the variable, and within square brackets you put the offset to how many steps you'd take to get to what you're trying to get to. So to get to the first, the offset is 0. You don't have to take any steps. It's right there. To get to the third one, you need 2 steps. So you put the offset within the square brackets. So back to repetition. Repetition is very heavily used for processing items within things, structures like arrays, for example. There are other structures, but we'll get to that later. So this is an example of repeating an action using a for loop, but this time around we're looking into an array. So we have an array called 10 integers, the size of 10, and those are the 10 numbers, 0 to 9. So we use the loop as before. Now the counter will represent how many steps we're taking through the loop, and we store, as we go through the loop, we store the value, whatever is in the array, in a variable called value, meaning some memory has to be allocated for that. And now there's std cout, that's just printing onto the screen. So I'll not get so much into that. The important thing to note is that within the square brackets, we use offset, like how many steps do you take from the beginning to the end. So I mentioned that, even as we've been looking at assembly, the assembly, or the way the computer works, is with addresses. And this is one of the things I wanted to highlight today as we go through, that we can work directly with pointers, which is the addresses. And based on the description I gave of what an array is, it's actually possible to look at an array using a memory address. As long as we have a memory address with the information of how big the steps should be, then we can be able to do the very same thing that we did before. So just to give us some space, let me. On the left is the code, on the right is the assembly, and I've put a link to Godbolt, but I'll not venture there at the moment, but it's something that you can look at later. If we look at lines, I seem to not have put the lines, but anyway, from where it's written MOV dword pointer, you see this RBP minus 64. And you can see the literal values 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these lines with the MOV dword, that is actually what the array is. And I seem to have copy pasted the wrong code on the left, but the point, I'll highlight the point that I was trying to get at. If you look at the RBP on the right, the first thing when we start a function is we push RBP, which is, it's a pointer to the base of the current block of instructions, which is called the stack. I'll get more into it a little bit later, but the core thing is that the way information is structured is, I talked about how there's a certain amount of space that is allocated. So the compiler translated the line 5 across to the machine code on the right. And if you look at the differences between the various lines, one thing that you will notice is that the differences in within the square brackets is RBP minus 64, and the next line is RBP minus 60, the next is minus 56. What you notice is that there's a difference of 4. That the compiler got that information from the size of an integer, which is known, which is 4 bytes. So that's how it knows the space of each and every memory location. So pointers are the way that we as programmers get to speak more closely to the code that we're writing, and we actually get into dealing with the memory. And there's a notion of that when you have a pointer variable, there's an expression called a pointer dereference, which is where you take a pointer variable, and when you add a star at the beginning of it, it means read the value that is stored in that location, which is what we have done here on line 9. Just a note, I'll update the slides, but as it currently stands, this is slightly not up to date because I did something slightly different. Let me see if Godbolt will play well with me right now. Okay, there the other program has loaded, but they'll do something slightly different. This is the next. Just a moment, copied the wrong thing. Yeah, so this actually is what the code is supposed to look like. I hope you can see the Godbolt screen. So in this particular case, because we're using pointers, the integer array, it's called 10 integers, but you can see we've allocated space for 11. The reason for that is we need an extra space at the end to illustrate this is the end, but we don't really use that value. We just use that value only for denoting this is the end of the array. So the numbers start from 1 all the way to 10. And on line 5, we have an integer pointer which points to that end. And you can see that I've taken the value 10 integers. Like I said, an array actually refers to a place in memory. So if you just take the name of the array, you're actually referring to an address in memory. So I was able to calculate the end location by adding 10 to the pointer. And the compiler knows that when you do this kind of operation, when you're working with a pointer, that if you add a certain number to it, an integer number to it, what you're telling it is jump this many memory locations, but of a certain size. So for integers, it's 4 times 10. So jump 40 bytes and give me the memory location at the end there. So we're able now to write a for loop, not with the offsets, but actually just with the pointers. So on line 6, we have where we establish the variable that we're going to be using to count. But in this particular case, it's a pointer, which points to the same location as 10 integers. The reason why we are taking a separate variable is because we don't want to keep on adding to the address of 10 integers. We want that to remain stable. But we need a copy or like a separate location where we'll be doing our calculations. So line 7 is the condition check, is pointer to integers equal to the end. Line 8 is where we increment, but that actually happens after. If you remember the while loop, the incrementing happens after. So what happens on line 8 actually happens after. Then we have whatever it is that you're doing within the square brackets. In this particular case, we're just simply adding up 10 numbers. And I've just re-enabled the output. So you can see on the screen here, this is what it would look like on a terminal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here's the machine code that we've been looking at. In this particular case, you can see that the last on line 17 is 0. So back to where we were. We had taken a brief detour to look at using pointers as the means for going through an array and performing some action. And pointers basically are just memory addresses. An array is basically or rather variables generally are just memory addresses. We may refer to them a certain way in our code, but the computer just sees memory addresses and just does the calculation between the memory addresses. So a very important structure in programming or even in the memory of the computer is the issue of strings, which is a sequence of characters. It's very foundational and it's very important. It's used in very many places. And basically, what a string is a sequence of characters. So in the previous array, we were looking at sequence of integers. And integers are of size 4 bytes. Characters are of size 1. So When we have a character pointer and we say we create an array of character pointers, its size, or rather the size is embedded in the pointer, meaning that the computer knows, okay, fine, that from the array that we're talking about is a sequence of characters, 1 byte each. So if I do base pointer time plus 4, I move 4 bytes. That's how strings are structured. They're just arrays of characters, which is of size 1 byte. I just wanted to make a quick note that the previous array that this is an array that I've created within the program, and its size is known because I'm the one who specified it. That's part of the reason why in the code I was showing on Godbolt, we needed to have a 0 to denote the end. So in the design of the language and a lot of things I will not get into right now, but there's a type of string called a null terminated string. It's used in places where we have, say, just a sequence of characters, and the way that we tell the program when to stop is when it finds the value 0. There is a way that we get to translate the characters that we see or that we know, that like what you're seeing on the screen, and that's the ASCII. There's a table, or like a very well defined table that maps certain values to certain characters. So that's kind of like what helps us with the computer. Even on the terminal, when we type into the terminal, whatever I type, say I'm typing hello world, as I type, characters are being added to the memory of the computer, and it knows when to stop when it finds a 0. So that's so I just want to just keep that in mind. I know many of you are experienced programmers, so you know about the strings that have a 0 at the end, but it's one of those things that can be tricky for those who don't quite understand what exactly is going on. So there is a special type of string called a null terminated string. You can either have that type of string or a string with a known size. So there are certain functions that take as parameters the address of the string and a size. So it knows, okay, fine, this is the start, I will only go 10 steps. So those are strings where we know its bounds. When we don't know the bounds, the 0 or the null value is what is used to terminate. But we'll get more into that later. So we previously created an array in the memory of the computer as it was running. And there's been this std cout thing that I've just been putting in the examples thus far, but I've not gone so much into it. But in this particular case, I wanted to point out that there's I'd mentioned literals before, and the literal that we've come across previously was the integer that we've been using in our calculation. But when we need to write something to the screen, std cout represents the terminal. But the point is that when we do std cout, we are getting feedback from whatever program it is that we've just run. So for example, I ran this program called tests, and you can see that there are the 2 lines that have been issued and then all tests passed. So whatever program this is that I just ran, put these words, all tests passed, 1 character at a time, into the output stream, which is the part of the program that receives output from whatever program it is that we're running. So it does so character by character. But in order to do this, it needs to have the stream of characters stored in memory somehow. So literals, we said that they're embedded into the program. So with the integer literals, we had them embedded in the instruction itself. But for strings, they're handled a little bit differently. And because this is a string of characters that is known when the program was being compiled, it is stored in a certain section of the binary that is generated when we compile as a sequence of characters. So when this program is run, it'll read this memory location and give that to the std cout. So it's something that you can see as we look at the assembly from line 6. You see we move this thing called lc0, which is on line 1 and 2, to a register called ESI. ESI meaning that it's storing a pointer. So point to where this string is, and basically call something called std cout. I'll get more into details of what exactly is happening on line 8 as we go along. But the point that I want to make at this point is that a literal means something that is stored within the binary. So these strings, when you write a string in your program, it has to be allocated somewhere within the binary for later use. So just like what we've been covering so far, this types like integer and character, I've not gone into the types like float as at now, but the point that I'm trying to emphasize in this presentation is that the size of what you're storing is very sensitive to how the computer is able to work. So we have an array of say integers. Like I said, it's 4 times 10 because the size is 4, but we have means, as even from way back when in the C language, of combining different types and giving it a name. In this particular case, I've written the C++ style, but there's a very slightly different way of doing it in C, but the essence is the same, where you can take different types and you put them together, and aside from some padding, which I'll not get into right now, the point is that the size of the type is calculated by the compiler. And if I was to now have, say, a pointer to this user-defined type, it would have a different size as opposed to an integer. So here's an example of the same, not as complicated as it was before, but this is how, like arrays of this particular type would look. So on line, on the left side, see we have this user-defined type. You can just imagine in this particular case, I've not, you can imagine it looks like this. It has this particular size. So we've created an array of 11 of these instances. So whatever the size of user-defined type is, you could have 10 integers, which is 40 bytes, then 10 of those. So the array of user-defined type would take 400 bytes. So this is something that usually has to be factored in, even in the assembly. So I think, let me see. Here's an example. In this particular case, I let it be empty, and because it's empty, it only has a size of 1, and which I think is what is being added here on line 5. So if I put in a couple of integers, let me see if that will compile that as just. then now the size that is needed for the array grows in relation to how much space is needed. So you can see, I believe should be this line 5 has changed, or the line 5, the assembly, possibly make that a little bit bigger. It has changed because of the size change. And if I reduce the size of what is stored in the compounded type, then the amount of space that is needed to be allocated for this type changes. So the point basically that is behind all of this is that the space, how much space is needed to store the information is very important for the production of the code that we're writing, and that is usually baked into the type. And an integer, or rather a pointer to a type, it may occupy the pointer to a type, or to the pointer of a type in memory is a variable that only stores where in memory that variable is, but within itself the compiler is able to infer just how much space would be needed or would be represented by that pointer. So I want to just take a little bit and talk about functions, what exactly they are in the machine code. And just like things like integers, literals, these are things that are baked into the core of the CPU or the operating system. I mean, it's something that is well established in the machine code. So in on CPP reference, if we look at the definition of what a function is, we get to see that a function is not an object, or rather, let me take a step back and look at an object. Like a function is really not considered to be part of something to be stored in memory, because it represents a concept that is actually much deeper in the computer. Let me see if I can find functions. Let me see. So functions are C++ entities that associate a sequence of statements with a name and a list of 0 or more function parameters. That's the definition according to CppReference.com. So we have seen functions before. Actually, a lot of what we've been dealing with actually have to be enclosed in functions. When we go to Compile Explorer, we need a function. The steps and the sequence of things that are actually being done by the computer need to be within a function. So it has a name and it represents a set of instructions. So when we write functions, we declare these are the instructions that are to be run, but later on in the program we have to call or invoke those functions to make those instructions be put in the running of the program, which we'll kind of like get into just in a little bit. So the function declaration is what we write as programmers. Say I intend my function to do this or that other thing. So what the bits that constitute a function are what it returns, which is kind of like the first thing that we state, the name of the function so that we can refer to it later, list of information that we are giving to the function to empower it to do what it is, the instruction that it's supposed to do. And finally, there's a list of instructions that are actually done by the function. So in this simple function that just returns the addition of two numbers, we have certain things that keep on recurring. This push RBP, then RBP, RSP, and then we have some instructions that are moving information. So this is moving something from EDI to this pointer, which is RBP -4. The next instruction moves something from a register called ESI into RBP -8. And if you notice, the difference between the two pointers is 4. And when the function is running, the information is coming from registers. So how information travels from the outside to the inside of a function is through registers. Yeah, so just wanted to make note of that. Then there's some instructions. Is the add instruction which adds what is a register called EAX, or rather what is in EDX to EAX and returns what is in EAX. So I mean, machine code is a lot more complicated, but I'm just giving you a guideline that even if you come to look at this later, if you see machine code later, the kind of things to look out for. So this is a very simple function, but this is what generally happens when we declare a function. But when we run the function, when we call the function, something else happens. And the thing with the function is that once those instructions are established, they're stored in a special place of your binary. And when the function name and the parameters are, I'll clarify if I come to say that parameters are what are stated in the function declaration. Then when you invoke the function, you give it arguments. It's a subtle difference, but just something to remember and keep in mind. So I have on line 4 of the code on the left a function. This is a function declaration. It's a declaration, but it's incomplete. It only states that there's a function called sum two numbers that takes two integers. This mechanism of declaring, there's a way to declare that a function exists. And as what we did in the previous slide is, this is a complete declaration. It's called a definition, where we add the actual instructions that are done. So just pointing that as an aside. But so in the main function, which is actually the main, or the function that is called to make a program to run, which is a function in itself. So I've set up on the stack, or rather in the function body of main, two integers, 10 and 15, which you can see established here with this MOV dword pointer and RBP 4 and 8. Those two values are stored in certain memory location on the stack. Then when we call sum two numbers, what happens is that those values are put in certain registers. In this particular case, it should be ESI and EDX and EAX. And because we've moved, or rather the way that when we are invoking a function from another function, the values that we're passing to the function have to be put in registers. That's why, there's a notion of pass by value, pass by reference, which we're not talking about so much today. What I'm emphasizing today is what happens like on the register level, what's happening deep down, is that the values have to be put in certain registers, depending on the architecture of the computer. And then we have a call to that function. So when the function is called, there's this bit of RBP. What happens is that when the program is running, there's a stack of functions that are put on top of each other. So when one function calls the next, the function that is called is put on top of the stack, meaning that its instructions are put on top and all of its information is put therein, and it starts running that function until it comes to an end. When it comes to an end, when the return happens, that function is removed from the stack and we go back to the previous function. So in this case, we're in the main function, but when we reach line 9, and we call this function called sum two numbers, the instructions of sum two numbers, as you see them here, are pushed on top of the main function. So that's how the CPU knows where it is. And once sum two numbers concludes, it puts the return value in a certain register, and it's called the stack pointer. There's all this happens within memory, so you can just kind of like visualize in your mind that the sum two numbers function goes away and the main function now becomes the top function. Then it continues from exactly where it left off, meaning like from this MOV. And you can see I've called the function 2 times. So the first time it's called, it'll be called with this value, the int first and second, because that's what I've passed. I've passed the value to that function. And in the matter of copy by, we have called in this particular case by value, meaning that the value that is stored in 10 is copied to another location that is established within the function. Each function has its own memory allocation to empower it to work, which is called the stack. So that's pretty much what's happening. So even when you read assembly, you may see a lot of things like to do with the registers, and then a call to a certain function. Then moving registers around and a call to a certain function. And when everything is done, the function kind of like releases its space. So when the computer is running, there's a lot of functions on top of functions on top of functions. Each thread has got functions on top of functions as the program is running. So just a quick note as we proceed is that functions don't have to have parameters. They also don't have to have return types. So there's the types of functions that just do things in the memory, but they don't have to return a result back. So those ones we start with the type of void, meaning that it doesn't return anything. Give it a name as usual, and call other functions. Is the std cout. I keep forgetting the name. Arrow. I know Emmanuel corrected me the other day. There's a message I saw. Left. Or chevron. There are different ways to describe it, but the point is when you see that, that's actually like a function call. Something that is defined within std cout, but I'll not get into that right now. So the core point I was trying to illustrate is that return types or the calling convention of x86 is that there are certain registers. I think the EAX is used for returning. The registers that are used for passing into the function, like it knows, okay, fine, look here, and all these things are established by the compiler. So just as an overview, you can see I've done hello world. So hello world is stored as a string within the binary. The string 5 plus 10 and equal to, this is just a sequence of characters which will be output when we call std cout. Sum is an integer, a memory location. So all this is embedded in the code when it's translated by the compiler. So I've talked a little bit about the stack, but now based on what I've just said, I want to introduce another concept called the heap, which is a section of memory which is not affected by this stack-based operation that is required for functions to work. One of the core advantages of C++ is that it gives us access to the stack. There are other languages like Java and C Sharp, managed languages, so-called safe languages, where everything you create, yes, the concept of variables and memory addresses is similar, but the difference between C++ and those languages is that things are managed for you. And the only way that they can be managed is in another section of memory called the heap, which is usually somewhere totally different. It's not affected by the memory allocations that are needed for the program to run. So C++ gives us that responsibility or power to manage things directly. So everything I've shown you, as you notice, is very closely related to the machine code. Like, yes, when you create a variable on the stack, it's going to affect the memory allocation on the stack and the like. But there are other languages that try to play it safe, and everything is allocated in another location of memory called the heap. So the heap, being independent of this stack mechanism, requires another form of responsibility, that if you ask for memory from the heap, say for example you want an array of 1,000,000 numbers, you can ask for that from the heap and say, allocate this much space for me, and if the operating system is able, if your system has that much memory, it'll gladly give it to you. But it's up to you to manage that memory. Secondly, that memory, being independent of the stack mechanism, can outlive the stack. That's why you have, especially when we're creating like large data structures, they're usually done on the heap because of availability of memory and independence of the stack mechanism. And when you get that space of memory, what you get back from the system is a pointer. Everything that is done on the heap is done through pointers, which is just memory addresses to somewhere in hyperspace, in the memory somewhere. It's a lot slower to get that memory, but it's a lot more flexible. And knowing that computers do process a lot of information, when we're dealing with large bits of information, a lot of the time the information is stored somewhere on the heap. So after talking about that, let's look at a function that takes as its parameters pointers, just pointers to somewhere in memory. So the same structure remains. For example, the add numbers array, it takes as a type an integer pointer, which is just a memory address, two memory pointers. And in the code, I've called it begin and end to kind of like state that what we are referring to is a range of memory that is storing integers. And any action that we do on that pointer, for example, if we add that pointer, it will go 4 bytes, 4 bytes, 4 bytes. So this on the left is what, say, this kind of loop would look like. It's similar to, there's a loop we wrote a few moments ago. The counter is an integer pointer, which is the same, points to the address of whatever we're beginning. We check that we're not at the end, and we keep on incrementing as we perform whatever it is that we need to do. So this this is okay. Whatever is between this the loop body is what we're doing over whatever size of whatever memory it is that we're dealing with. So in this example, I've created I've stated that the data size is 10. I'm just doing 10 integers. I create an array, but this time on the stack using the keyword new. I mean, not on the stack, on the heap, meaning that this particular piece of memory, as you notice, the assembly doesn't have the RBP minus structure that we had before. It does store the variables that are used within the, just to process whatever it is that we're doing, meaning the begin and the end are space is allocated for them, which is just 4 bytes, 4 bytes. Actually, should possibly be more, because we are likely dealing with a 64-bit system. So also, just as an aside, you notice that in previous versions of the assembly, we had registers like EDI, ESI, and the like. The reason why, or rather, the way I can describe it is that RDI is the same register as EDI. The difference is that RDI, the R denotes 64 bits. EDI denotes 32 bits. The reason why it has come out this way is because this time around we're getting from the heap. So it depends on the size of the machine. The previous examples, I believe, let me see if this is, yeah, so in the previous examples, like say here in the function declaration, because the compiler is able to reason that we're only dealing with integer types, and we're also on the stack, it gives us a smaller register, or a smaller view of the same register. So I just wanted to note that the size of whatever information you're dealing with is very important to, I mean, the programs that we write, or to the compilation process. So based on all of that, there's a function that does something to a range of numbers. And then, just as an example, we create that on the stack. So with this int star data that's on the stack, then we're able to get the end of the data by just adding the size to the pointer, meaning it will calculate what the memory address of the end there is. And then now we store the result within our space. Result is a variable within our space, and we delete the array of data that was allocated. So it's our responsibility to delete what is allocated on the heap, which, as I'm sure you all know, or rather those who are a bit more experienced know, that is a big source of a lot of errors and bugs. Working with pointers is very hard. That's why C++ is considered unsafe. It's very powerful. It's more powerful to be able to deal with the memory yourself, but it requires a lot of responsibility, which unfortunately has been abused, and that's why languages that deal this low with memory get a bad reputation. So the point basically in this slide is that this the main function is the owner of the data, and it passes pointers to the data when it calls the add numbers function. So that the add numbers just uses the memory locations to do whatever it needs to do, check and add, and check and add. And that way, we don't have to pass all the data. I don't have to copy it into the function for add numbers. As you know, I mean, computers can store a lot of information, and we don't want to be spending all the time copying a lot of information into the function that does whatever it is that we want to do, because that, one, creates a slow operation, and two, it may not fit. That's what we're differentiating between the stack and the heap. So the point to keep in mind is that this space, or rather like a function or this function stack, can only store so much, and a lot of the times we have to deal with information that is widely, or rather takes up a lot of space. So pointers are a mechanism to refer to memory addresses somewhere else in order to get the data that we need and be able to operate on it. So this particular case, we're doing integer pointers. So thus far, everything we've talked about, apart from the std cout, is virtually C. It can work in C. You may have to change a few functions here and there, but in actual sense, all of that has mostly been C. And now let's start talking about C++. We're putting the plus plus into that C that we just talked about. One of the major features, and see the reason why I've actually gone into all of that is that a lot of concepts in C++ are actually very hard to describe from scratch, but you kind of like need to go down or back to the history a little bit to make a bit of sense, or rather to be able to better explain the concepts of today. As you note, I've not said anything about iterators yet. So one of the things that C++ brings to the table is custom types that we define ourselves, and that's how we get to extend and to bring more concepts of the world into our programs. Like I mentioned before, things like integers and floats, and those are things that are hard coded into the system. So C just refers to what is there. In C, we used to be able to do structs, which we could create the compound types and give pointers to those types of types. And a lot of C is it revolves around that area, but it doesn't allow us to add functionality or to create types in the actual sense. For example, like integers behave in a certain way, meaning they have the amount of space that they take, but they also have features like how they operate. When you add an integer to another integer, that is something that is baked into the system. C++ allows us to create structures or types where we define how much space they need, and also things like what they can do or can't do. So another topic, another concept I just want to touch on that C++ gives us is the concept of templates. Templates are a mechanism to extract or to generalize some instructions, and in such a way that, okay, we can maintain the instructions that are to be done, but we can remove the type information to be put in later. So templates, they're templates, as the word template means something you can look up in the dictionary. But the point in programming terms, a template is like a recipe for a function that is lacking the information like how much space would be needed. So for example, in this function here, we have, this operates on integers. So the system knows, okay, I can calculate RBP, and these are the steps that I will need to take because it knows the size. But templates allow us to write the same function but extract that part that has to do with the size. Meaning that when you write a template, the machine code cannot be generated from it until you give it a type. And the type will now give the information, the size information that is needed, and now the machine code can be generated because now the system knows how much space to allocate, how much is needed to generate the actual machine code. So the reason why I've touched on that is that in C++, we operate with a library called the STL, which means Standard Template Library. Keyword there being template. In that there is code that has been written, many algorithms, many complicated things have been written, and the only thing that they're missing is the type information. So for example, there are containers. So I've gone back to the top level of CPP reference, and then we have the containers library, which extends the functionality, like what we're talking about before, like in C was arrays. And yes, I know in C it's possible to implement things like linked lists and the like, but the point I was illustrating is the issue of the size of the memory and the like. So when we go to the containers library, we say that it's a generic collection of class templates and algorithms that allow programmers to easily implement common data structures like queues, lists, stacks, and the like. So they are sequence containers. Sequence containers are very similar to the arrays that we're talking about before, but they have other special things that they do. And then you have associative containers, but I'll not go so much into that. I'll just kind of like keep it to the sequence containers. So we have a C++ template called an array. We have a vector. A vector is actually like something that is very, very commonly used. It should be like your default go-to structure. So these are structures that store data and give methods and things of how to work with data. So if you look into, say, vector, the first thing that you notice is that it's a template class T, meaning that it'll be working on a type which is represented by T. And there's a default constructed type, which is the allocator, which this is something that creates the memory automatically within the vector. So for those that don't know about vectors, vectors are like arrays, but another word for vector is it's a dynamic array. Previously, so we had to specify and say, okay, I'm allocating 10 integers, but a vector is it can grow and shrink as you go, meaning that it does a bit of clever things with memory, but it'll store a sequence of whatever type T, whatever size that is. So a vector doesn't exist in machine code. You can't take a vector and say, oh, here's the RBP, RSP, because it doesn't have the size. You have to give it a specialization. So as you can see here in the example in Compiler Explorer, we specify that this vector is of type int. So it will create memory just like what we're doing with integers before. So this is something, of course, one needs to look at later. But so I went through all of that to illustrate this concept of the size. How much memory is taken is very core to what it is that we do on the computer. And yeah, so that there are many types of containers, which I can't get into right now, but just keep that in mind. So what are iterators? This talk is about iterators, and I have not mentioned iterators until all the time up until now. Iterators are types that behave like the counters we were saying before, or that behave like pointers within the array. They redefine the addition, comparison, the operators. Basically what you can use to work on a pointer. They behave like pointers. Earlier in the definition in CPP reference, when we're talking about iterators, we said that they are a generalization of pointers that allow a program to work with different data structures, for example, containers, in a uniform manner. And you've seen that the containers themselves also require some information. Like to create a container, you must give it information of what type you're dealing with so that it knows how much space to work with. And once it has that information, then it can produce the iterator that points to the data. So iterators are actually types that are produced, or rather given to us, by containers to describe what the container holds within itself. That's kind of like a high level description of what exactly iterators are. So they're similar to pointers. They point at memory, but there are things that we get from the containers to tell us this is where the data starts, this is where the data ends, and that is now what is used by various algorithms to do different things. So it's earlier we said that it's a way of joining the data to the algorithms. So let's get more into that, even as now we're now in C++. This is a rough idea of what an iterator looks like. Remember I said it's a type. And it needs to hold, it needs to know the shape and the size of what it's looking at, so as to be able to navigate like that collection of memory. It needs to know how to navigate that memory. In the case of the simple arrays that we've been talking about, the operations basically are, okay, fine, there's a starting point, say the begin iterator. It has an operation of incrementing, add by 1, which can be manipulated, can be extended using the C++ operator operator overloads mechanism to actually even do different things. But the standard, the idea generally is that it goes by the size of the data that is being pointed to. So in actual sense, a pointer is actually the most basic iterator. The pointer we've been talking about all of this time is the foundational iterator. Like anywhere that, any place that is asking for iterators, if you can literally use pointers to a certain type. And when I say pointers to a certain type, what I mean is that we're talking about, say, like an array, because a pointer to a certain type can be used to denote an array to that type. So, but C++ allows manipulation of that type to do different things depending on the creator of the iterator. So you don't have to understand a lot of what's going on here. This is pseudocode. It might be wrong or it might be right. But the core point is that the iterator, it's a type that may hold, say, the base memory, and it exposes a comparison to, for example, to find out, are we at the end? It has to support those operations. So the two core operations are we at the end? How do I go to the next location that I'm supposed to be pointing at? So these types, or rather, I just wanted to touch briefly on where, I mean, iterators are not things that we write or we're meant to be writing ourselves. Okay, if you have a certain level of skill, you should be able to write it. But the point is that C++ has this mechanism. All of the containers are designed in such a way that they tell you about their iterators. So when you create a container and you call a certain method, the method is called begin. It's always defined somewhere. Yeah, so there's a method called begin. When you call begin, the container looks within itself, looks within its memory and its internal structure, and gives you a type that has information about that location. And that type now is what you use to look at what is inside that type. So if we just go back a little bit, back to this section here, this where we talk about a function that operates on array pointers. So a typical algorithm will take iterators, meaning the beginning and the end. So beginning iterator, end iterator, that is how we describe a range. Like there's a memory location starting here to here contains this particular type, and we get to be able to look at what is in there. So with pointers, we use the star, the star, the dereference operator, which is a star and the name of the variable, to look at what is in that particular memory location. And you remember that the pointer knows what type it's pointing to, so it kind of like knows that, okay, it's a certain memory address for the next 4 bytes is my integer. I'm able to look at the integer. So iterators are types that hold this information but behave exactly like pointers, or rather they have an interface of pointers. So they just need to have the dereference operation and the increment operation in order to reveal that information about where they point to. So this generalization empowers us to have different types of data working in different types of algorithms using this agreed upon communication method. So there's the star method and I mean the star operator and the plus plus, meaning go to the next, and the like. So that's an illustration of what iterators are. So there are things that you may not have to write them or understand every detail about them, but what you need to know is that they help us look at data in different types of containers. So I did mention about ranges, which just represent like a starting point and an ending point, but it doesn't tell us anything about how things are stored inside. So the ability to override, for example, the plus plus operator gives us the ability to jump around even in different ways. You can have an iterator that is designed to jump. For example, if you have a list of 100 numbers, it jumps every 10 numbers. But to the outside world, all we do is plus plus. And within itself, it just gives us a memory address. Remember that the most machine code just deals with addresses. It doesn't really care about all of these high level things. But these concepts are very powerful. So here's an example of a container. This is a vector of integers. And I'm able to get a variable pointing to the iterator designed for the vector using the begin method. It gives a copy. So it's actually an independent thing. You can add it. You can have 10 different iterators looking at different parts of the vector. So this is just a simple while loop. Just like before, I decided to use a while loop here just to illustrate. But generally we use the for loop. So let's now talk about algorithms. I've mentioned them here and there. So algorithms are special functions that do operations on a range of objects. And they are defined in terms of operators, meaning that the parameters they take in are iterators. Iterators meaning essentially memory locations. And yeah, so they have a begin and an end. So there is a section where you can kind of like go and look later on CPP reference, where there's the algorithms library. So these are a collection of algorithms that have been studied and researched on for many years, tested, and many people have agreed that these are important algorithms. And the structure is that, let me see count if. This is what it looks like. They look a bit scary, but first and foremost, they are templates, meaning that they can be used with different kinds of data. So so the templates, and the first parameter, I mean, there's a within the sharp parameter, the sharp angled brackets, is the types that can the type parameters. These are substituted with types, and within the round parameters. Now those are that's the how the function looks. So these are mostly function signatures or function declarations, but they're implemented in the standard library of whatever compiler that you're using. So to use these types of algorithms, you just need to have a place where your data is stored, take the iterators to where that data is stored, and give it to the function. And it's able to deduce based on the type of data and in the container what to do and how to kind of like respond to what you've given it. So I've gone through all of this journey to give kind of like a foundation for exploring the C++ library, the templates for data storage, but also the templates for working with the data. So here's an example of how that would be used. So at the bottom, or rather at the top, you can see on line 2, we create a container of vector of integers, meaning that it knows its size is 4 bytes, size being the core thing here. And actually, I just gone to the countif method, and what you see that we do is that we take the myInts.begin, meaning the beginning iterator, the start of what is stored within the vector of myInts, and we give it as a second parameter the ending iterator. The third parameter is actually a function. It's not a function. I'll actually not call it a function. It's called a function object. It's an object. It's a special class or object that behaves like a function, but it's not a function like what we were talking about before, where we have the RBP, RSP. In essence, it acts the same, but it's an extension of the idea of a function. It's a C++ thing that makes us treat a function like an object, meaning that you can create a function of a set of instructions and give it to the algorithm and to tell it what to do. So in this particular case, this function takes an integer. As you can see, we're dealing with integers. So it's a function that takes an integer and does a comparison and returns whether whether it was true or not. The name of the algorithm is CountIf. So it has within itself, it has like a counter. It'll count it'll count whatever you're iterating over if the current value returns true. If it returns false, it doesn't add. So in this particular case, we get the result stored in the number of even numbers, and we output that. So traditionally, you can see, okay, now this is kind of like the way it would be written before. We have the array of integers, variable to store the result, and a regular for loop. So within the CountIf algorithm, there have been carefully written loops. At the end of the day, like if you look at even the source code, it'll have a for loop, but the for loop has been tested and been analyzed a lot more than any loop that you'd write by yourself, because repetition, computers are so fast that any small issue in your code is very hard to diagnose, because it just wants that you give it the data and it goes through really quickly. So as part of the C++ way of dealing with templates, templates allow us to extract the type from the functions that we are writing or the classes that we are writing, but there are ways to analyze a type. For example, we may have a container that we don't want to store floating point numbers. So we can constrain the template and say don't only store integral types. If somebody tries to create an instance of this template function or template class with a type that doesn't match, no, it doesn't allow. So it's another level of programming that we have, to express ourselves a lot better. So another thing I just wanted to touch on, of course we've been mentioning it, or rather we've been overlooking it for quite some time, is what streams are. So a stream is, it usually refers to a sequence of characters or bytes going to or coming from the outside world of our program. So there was a point earlier I was illustrating with this program called tests. Tests doesn't take in any information, or rather it possibly should. Yeah, so the tests, this is a test that is generated by it's a catch test generated for some project, and the binary itself has options that you can pass to it. So for example, when I did tests colon H, the colon H is a sequence of characters that the program will receive and read when it starts to figure out what exactly it wants me to do. So if I don't pass it anything, it takes a certain path. If I use one of these methods and options, it will pass what I fed it and figure out what to do. So this is how I communicate with the program with a sequence of characters from the terminal and tell it this is what I want you to do. And in return, all the characters that have been printed on the screen. So for example, from here where I invoked tests, all this is just a sequence of characters that has been generated by the program by like the std cout, something that has been programmed like, okay, fine, if somebody asks .h, put these characters on the screen. So the reason why I've brought that up is that the streams are a source of data, and they are also a destination for data, meaning that when we need to deal with lots and lots and lots of data, we may not be able to store everything within the program, but we may have to read in from somewhere, and we need like iterators to be able to help us to do that. Earlier, you heard me mentioning about the null terminated string, and that's kind of like how if you tell the program like read in characters, it can read them in for such a long time until it finds a null that tells it, okay, fine, stop. That's the end of whatever data that you're reading. And there are iterators that are able to understand streams and treat streams as they would treat an array. So it's just something that I wanted to mention, but something that of course you need to explore. And as you explore, you do so with the understanding that yes, you're working with templates, and the idea of templates is that you need, it's just a recipe, but it needs the ingredients, or the core ingredient, meaning what is the data that it's working with and what the size of that data actually is. So I was thinking of going over a few exercises from the advent of code, but I think we might not have the time to do that. But I did kind of like prepare like an exercise. So it's something that if you have time, you can look at this particular link, and it should take you to something that you can kind of like try and see Just a moment. And see if, like, based on what we've just talked about, if you're able to solve the problems. It's you may need to fill it's a project that has been set up, so it's just something experimental. You can kind of like give it a try and see if it's something that, if it's a format that we can kind of like be testing out what we've kind of like learned, or like as a challenge. So generally you have to fill in like the missing bit. This is supposed to be, there's a piece of data here, which is basically just an exercise that takes like a sequence of numbers and separated by spaces. And I think you're supposed to add up the different sections that are separated by spaces and calculate the highest, to calculate the highest, the highest collection, or rather the collection with the highest sum, so to speak. So in this particular case, it needs to go through, say, this section and add these numbers and then store the result, go through the next section of numbers and then store the result, and so on and so forth. So the idea is, in this particular case, just to enable us to simulate information coming from the outside world, I've put it into a string, and I've created a stream out of that string. So this stream is an input stream similar to std cin, which takes information from the outside world. You give it like numbers and the like, but in this particular case, you do input, or rather input stream. No, the point, yeah. So the point is, you take information from the stream. Sorry, I did that a bit wrong. You're taking information from the stream. So now you see what the arrows mean. They mean coming from the outside world into the program. So I could put this in a string. I could kind of like have a variable here, say std string my variable, and I want to read from the outside world into my variable. So the point is, this is just an exercise, like solve this problem, and when you're done and you're happy that your solution is working, you can always share. You can share the link to the completed code by going up to where it says share, copy the short link. It should generate a link for that particular piece of code, and then you can paste it in the Discord or in the comments, just wherever it is you're watching this from. So I believe I'll leave it at that for now, because my main purpose was just to illustrate the concept of space that is required for storing the data, and the relationship between that and iterators. Why iterators are you need to understand the concept of where information is stored and how much space that it takes in order to kind of like have an understanding of iterators. So I think I'll close at that for now. Thank you very much for your time and your attention.